All right, so we're on to review for number 19. Which of the following pairs of molecules and predicted bond angles is incorrect? So this is testing your bond angles. And here we have a Lewis structure that has a steric number of 5, right? Let's get all the steric numbers. This one has 1, 2, 3, 4, 5, 6 bonding sites plus lone pairs, steric number of 6. This one has 1, 2, 3 bonding sites, steric number 3. This has bonding steric numbers of 1, 2, 3, 4. 4 bonding sites, no lone pairs on the central atom. So steric geometry for all of these, we can write out, and we'll also write out the molecular geometries. And so the molecular geometries, steric geometries are just straight from the steric number. So you got to know these. This is the most favorable way to put 5 atoms in 3-dimensional space as far apart from one another as possible, minimizing electron-electron repulsion. It's a trigonal bipyramid. For steric number 6, octahedron. Steric number 3, it's a trigonal planar. And steric number 4, it's tetrahedron. Tetrahedral. Okay, if we have lone pairs, our molecular geometry is not going to be the same as our steric geometry, right? And so we have 3 lone pairs here. So what happened? You started with a trigonal, there's a triangle, bipyramid, one on top, one on bottom. You now remove 3 of the equatorial, the trigonal sites. So you remove 3 of those because you have 3 lone pairs. What are you left with? You're left with a line. Molecular geometry is linear. That's why, guys, if you can understand and visualize this a little bit, the memorization isn't that bad. I know it seems like a lot, but the names are very good. They make sense. And so, you just have to practice visualizing this and, use the resources online that I gave you under the Exam 3 resources section. There's some great links to some 3-dimensional modeling tools that are online apps that you can use. Octahedron. Octahedron looks something like this. You have your central atom. You have a square plane going like this, and then you have a cap on top and a cap on bottom. And now you've removed one of those caps. So what are you left with? You're left with a square pyramid. So square pyramidal molecular geometry. What about this one? Trigonal planar. No lone pairs. They're the same. Steric geometries and molecular geometries are the same. And same with this last one. Okay, so now we just need to look at the bond angles and see if this makes sense. Linear, 180, better believe it. Things in a line are 180 degrees. Square pyramidal. Well, anything in an octahedron is 90 degrees. These are right angles here. But we have lone pair there pushing these. Remember, lone pairs take up more space. So it's going to cause these bond angles to contract and be some value less than 90 degrees. We don't know what, but it's going to be some value less than 90 degrees. So that one's correct also. Trigonal planar. It's trigonal planar straight up. There's no lone pairs. Trigonal planar is 360 divided by 3. It's equilateral triangle, right? Equilateral triangle right there. 120 degrees is correct. Tetrahedron is not 90 degrees, guys. 360 divided by 4 is 90 degrees. I know it seems tempting. That would be a square plane. It's not in a square plane. It's 109.5. Okay. Why is it 109.5? Some people ask me that. That's an interesting question. We could do the math to show you why. It's 3-dimensional geometry, and most of you probably haven't done a lot of 3-dimensional geometry, even though you can, right? But that bond angle is 109.5. Is it exactly 109.5? No. Okay. We could do the geometry and actually get something that has some roots in it. I think a root 3 is in there somewhere. That gets you the 109.5 exactly. But anyway, it's about 109.5, and that's going to be the one that's wrong there. So the answer there was D.